Real-world data rarely arrives in a neat mathematical state. It arrives as a swarm of individual responses, full of hidden collisions and overlaps. Consider a municipal survey trying to determine the distribution of household appliances in a single city. This diagram outlines our raw data. The survey finds 75% of households have radios, 65% have irons, and 55% have toasters. It also captures overlaps. 50% have both radios and irons, 40% radios and toasters, 30% irons and toasters, and 20% have all three. This data presents a specific problem. If we randomly select one household, what is the exact probability they own at least one of these appliances? And conversely, what is the probability they own exactly none of them? Faced with this, a beginner will typically rely on intuitive arithmetic. They simply add the base percentages together. The sum of 75, 65, and 55 is 195%. This breaks reality. A foundational statistical axiom is that the total probability space, denoted as S, represents all possible outcomes. Its total probability must equal exactly 1, or 100%. Our arithmetic failed due to hidden overlapping logic. A household with all three appliances was counted 3 separate times. We must translate these numbers into a topological map. We establish a boundary. Everything inside this box is our sample space of 1. Simple addition is useless against overlapping logic. To calculate the true probability, we have to partition this space visually and strictly define its overlaps. To build these rules, we pause the appliance survey and strip the complexity down to a simple, discrete experiment, tossing a standard 6-sided die. This grid visualizes our sample points. A sample point is a single, simple outcome of an experiment, in this case, rolling a 1, 2, 3, 4, 5, or 6. Outcomes are considered mutually exclusive if they cannot occur simultaneously. You cannot roll a 1 and a 2 on a single toss. These 6 individual outcomes are also exhaustive, meaning that combined, they make up the entire probability space. At least one of them must occur when the die is tossed. We can construct compound events from these points. Let event E be rolling a number less than 4. Let event F be rolling an even number. Notice that the number 2 exists simultaneously in both sets. This shared space is the intersection of the two events. Our goal is to find the mathematical union of these sets. We want the precise probability of rolling a number in event E or event F. To find it, we rely on the principle of inclusion-exclusion. This is the formal additive rule used whenever events are not mutually exclusive. Watch the geometry. When we shade event E and then shade event F, the intersection in the middle becomes double shaded. By executing the final part of the equation, we subtract the exact value of the intersection. We eliminate the double counting, leaving the entire union uniformly counted. This simple principle scales. It is the engine for calculating the union of any set, no matter how many variables are involved. Mathematical rigor demands that we isolate and subtract overlaps. Failing to do so compromises the integrity of the total probability space. Returning to the chaotic appliance survey, we map out radios, irons, and toasters within our sample space.
There is a singular rule for navigating multivariable compound spaces. You must solve the geometry recursively, from the deepest intersection outward. The deepest point in this data is the group of households possessing all 3 appliances. The raw data establishes this intersection at 20%, or 0.20. This anchors our map. We step 1 layer outward, to the intersection of radios and irons. The raw survey data states this total overlap is 0.50. To find the households with radios and irons, but specifically not toasters, we take that total 0.50 and subtract the 0.20 center. This gives us 0.30. In set theory, this specific isolated region is defined algebraically using complement notation, written as the intersection of R, I, and T prime. The prime symbol denotes the complement space. It means the data mathematically excludes that specific variable. We recursively apply this inside-out subtraction to the radio and toaster intersection. The raw 0.40 minus the center 0.20 leaves a mutually exclusive petal of 0.20. We apply it again to the final iron and toaster intersection. The raw 0.30 minus 0.20 gives us 0.10. Now we step to the outermost boundaries to deduce the households containing exactly one appliance. To find the radio-only region, we take the raw top-level total of 0.75, and we subtract the 3 previously calculated internal pedals, 0.30, 0.20, and 0.20. This reveals that a mere 0.05, or 5% of the households, have only a radio. Applying that same logic to the remaining boundaries cleanly populates the rest of the map. This chart shows how this partitioning logic is identical to a structured probability matrix. The rows and columns of disjoint probabilities must perfectly sum out to their marginal totals. Complex probability spaces are never solved by raw calculation. They are solved by recursively isolating mutually exclusive subevents, working from the deepest intersection outward. Here is our fully populated diagram. With the space strictly defined, we can finally answer the opening questions. First, what is the probability a household has at least one appliance? Because we broke the data into mutually exclusive regions, we can use simple addition without fear of double counting. The total union of all 3 events is exactly 0.95. What is the probability a household has none of these appliances? We look to the negative space outside the union, but within the sample space box. Since total probability equals 1, this outside region is 1 minus the total union, leaving exactly 0.05. This diagram shows the formal algebraic theorem used to define this exact negative space, DeMorgan's laws. The first law states the complement of a total union equals the intersection of their individual complements. In our data, not having any appliance is exactly the same as not having a radio, and not having an iron, and not having a toaster. DeMorgan's laws perfectly invert logical propositions. The logic scales flawlessly, whether you are sorting 2 overlapping variables or 100. Treating raw data as rigid geometric sets governed by rules of intersection and complement is the only way to bypass flawed intuition and arrive at absolute mathematical truth.
Are you sure you don't want to like, subscribe, and share with your friends? Jealous.